just 2 words. Hello, everyone. Welcome again to our tea break TH Colloquium. It's really a pleasure to have Giuseppe Mussardo today, and Alessandro will introduce him with a small video, even if maybe we don't need it, but let's go on.
Yeah, indeed. Maybe Giuseppe needs very little introduction. He's one of the most eminent statistical physicists of our community. He's a professor at SISSA since a few years now. And he gave very important contributions to several branches of theoretical physics, mostly related to statistical physics, the theory of S matrices, integrable models, several approaches to quantum field theory, out of equilibrium quantum field theory. And most recently is also went in a slightly, maybe, if not different direction, a perhaps more surprising direction for people that are more used to traditional topics, because he's been looking at the relation between very deep mathematical structures and physics. And this will be the topic of this of today's talk. It will be an overview about the proposed relation between the generalized Riemann hypothesis and the Brownian motion. So please, Giuseppe, tell us everything about it.
Okay, thank you. First of all, thank you very much for the very kind invitation. It's a pleasure to be here and to tell you about it. Now, Karl Kraus, a famous writer of the Wien or the fin de siècle, used to say that a scientist is the one who knows how to get a solution out of an enigma. So what is the enigma of today? Imagine that you had the chance to meet Dr. Riemann in 1859, and he would tell you that he has found a wonderful function in the complex plane that, according to his calculations, seems to have the zeros, at least some of them, an infinite number of them, aligned along the real axis equal 1/2. Now, this enigma became really a puzzle when a few years later, imagine you had the chance to meet Dirichlet, that was also a colleague of Riemann in Göttingen, who reported to you that he has found another function that has the zeros on the axis 1/2, although the imaginary part of these zeros are different from the previous one. And then he came the next day and say, well, I found another function that has also the zeros on the line 1/2. And then another one, and another one, and another one. So, in short, there are infinitely many functions that I will describe in detail later, which apparently has the zeros along the line 1/2. Now, I want to convince you today that there is a very simple, elegant, universal explanation of this fact, which employs a very famous and basic example of statistical physics, which is the Brownian motion. Now, I remind shortly that the displacement of the Brownian motion, or better, the quadratic displacement of the Brownian motion, and taking the square root of it, otherwise will be 0, the average, grows exactly with the critical exponent, which is this 1/2. And I want to, of course, convince you that these are not, is not something, there is a deep reason for that. Now, moreover, behind the random motion, there is a very basic and very rigid, I would say, object in probability, which is the normal law distributions, which has an incredible stiffness. What I mean is to not having a normal distribution law in a set of data, you really need to work hard. Let me put it this way. I will be more precise later. Now, concerning the Riemann hypothesis itself, mathematically speaking, there is a very important epsilon. So what you have to prove actually is that the displacement of the random motion I'm talking about or the supposed random motion I'm talking about, goes like n1/2 plus epsilon, where epsilon is an arbitrary small positive parameters. Now, for a physicist, this is very welcome, because we are very familiar with the epsilon expansion and this and that in other contexts. This epsilon is nothing else but logarithmic correction to the leading power law I was talking before. And we will see later that this behavior is really very natural in it. Now, before going on, I have to make, let's say, a disclaimer and also a series of comments. What I have to offer later in this seminar is not theorems, or at most, if they are theorems, are of probability measures. However, as a physicist, we have a clear distinction between theories and theorem. Now, let me dig a little bit on that. If I show you F equal ma, you will not ask to prove this equation. This is a theory, it's not a theorem. But once you have a theory, you can explain nicely all the motion on Earth and heaven. Now, the same is true for Maxwell equation. Now, this, once again, are theories, part of a theory. And once you got them, you can, in one shot, understand an enormous number of phenomena coming from electromagnetism. Now, Schredinger equation is the third example. I mean, this, once again, is part of a theory. And once Schredinger got this, together with all the friends of that time, you can explain at once an innumerable number of facts, even curious, which come from quantum mechanics. Now, I want to say that for a physicist, a successful theory has to be simple, elegant, universal, and it must accommodate all known facts. It should be able to predict new ones, but most importantly, we should be able to falsify it, namely to test it to all possible degrees of consistency, let's say. Now you will see how this all this will fit in the next of the talk. Now, a paradigmatic example of what I'm going to say can be this one, which actually appear later in my consideration. Consider the so-called square-free numbers. These are the natural numbers whose prime decomposition has no multiplicity. So for instance, 6 is a square-free number, 14 is a square-free number, and so on, but 4 or 9 are not square-free numbers. Now, consider this set of numbers, natural numbers, and imagine that you ask the question, what is the density of square-free numbers among the integers? Now, the way I would argue is not my argument, but I'm just presenting how I would argue, and how I will argue in the following is the following. Assuming that there are no correlation between numbers, something that I cannot prove, at least not me. 1 over p is the probability that a random integer is divisible by the prime p. What I mean is, I make probabilistic what is a deterministic property of the integers. Because any p numbers, 1 is divisible by p. But I assume to be a probability rather than a deterministic property. But once I assume that, of course, 1 minus 1 over p squared is the probability that the number x is not divisible by the prime more than 1 time. At this point, of course, I can have a bold idea what this density could be. Would be the product of these elementary probabilities as far there are no correlation between primes. So this part of the story is a theory, if you want. But then, of course, nothing prevents to have a theorem, because this infinite product is the Riemann at the position 2. Of course, this you can compute it. And finally, I have a very bold conjecture what this density has to be. At this point, I can check it. So I say, is it true? Well, what you can do is just experimental mathematics. You just generate all the integers and start erasing all the square-free numbers. The most you can, of course. Then you see how they scale with n. But you convince yourself that is enough to have very, very few hundred of them, that this density converges spectacularly to 6 over pi squared. Okay? So this is, if you want, my physical way or a physicist way to argue about the Riemann later on. And I have to say that this kind of physics approach, I mean, approaches coming from physics, has been used in the past very successfully and very, how to say, very, provide a very beautiful set of ideas, in particular by Michael Berry, that I have a really pleasure to welcome because I see him in the audience, which has made its spectacular contribution in these topics, although different approach to what I'm going to present today to you. Now, this has been topics of a series of papers that I wrote with my close friend and collaborator, André Leclerc. So in the past, there were 2 of these papers. And more recently, there is really a long paper devoted probably to the most difficult part of this story, which is the Riemann itself. So if you're interested, you can browse this paper for all the details. Now, what are the topics of my seminar? I will talk about randomness versus determinism, which is really crucial to my stories. I will tell you then what is the Riemann hypothesis, the Dirichlet character, later L-function, all that, the generalized Riemann hypothesis, and finally, I will tell you for whom the bell tolls. So let me start with this randomness versus determinism, which is much less sharp than what one can think. Now, in particular, number theory. Now, number theory usually is considered as a field which is ruled by very strict, deterministic, and military law, I would say, of arithmetics, where randomness seems to play no role. But is it really so? Now, I want to really bring a couple of examples which will undermine this certainty. An example are 2. I can provide others, but I just choose 2 of them. One is some arithmetic tales which come from the world of pi. Others are the strange realm of large numbers. Now, let me talk about law and disorder in pi. Now, pi is a remarkable number which has a stunning, beautiful formulas that you can predict what will be the next term at once. This is one. This is the famous Wallace infinite product. There are spectacular convergence series in terms of the Fibonacci and this and that. Now, no doubt that pi is incredibly ordered number. However, imagine that you take another point of view. You take a basis. What I'm going to say is in digit in 10, in the basis 10, but you can repeat it in any basis you like. So you expand the number, and then you say, well, what are the numbers of each digit in certain decades? So you start doing really humble statistical analysis. And you realize that the number of, each digit appear exactly the same number of time, any interval you consider. So this is how he looks like if you take 5 million digits as I did. Now then you go again to pi and you start picking numbers in a period. I choose here 6, but you can choose any period you like. You take the numbers you got in this way, you make statistics, once again, completely uniform. You come back to pi and start picking randomly. So you just jump one number from the other, you repeat the analysis, once again, uniform distribution. So, this means there are no correlations, essentially. For a physicist, it means there are not many correlations. There are correlations, of course. Each number is deterministic. But if you take this point of view, there are a bunch of uniform distributed numbers. At this point, you can ask, what is the displacement function of this? The average, of course, is 4.5. You construct this, and you just make some experiment. I did this with 20,000 digits and invite you to repeat it the most you can. You see that immediately appears some normal law, okay? Now, I have no theorem on this. Probably there are mathematicians, I'm pretty sure that they have done much work. And this is just an experimental mathematics I did myself with this even a very, very small number of samples. Now, let me talk the other example. Imagine you take an integer, you decompose, and you define an arithmetic function which counts the number of distinct prime divisors without multiplicity. So you just say if a number is kappa prime, no matter how powers, this function is kappa. And then you ask yourself, what is the average of this function and how is distributed? Well, you can do some experiment. Once again, you have to go very large numbers, say 10 to the 60. You start computing these numbers and you start collecting integers. Now, with a bit of trial and error, you realize that the average of this number seems to go to log n. Now, I want to draw your attention that this means that an integer of the order 10 to the 1,000 essentially inside there's only 7 different primes, no many more than that. Now, when you do the displacement of this function, what you realize is Gaussian, and in this case, this result is a dignity of a theorem, is the celebrated Erdos-Kass theorem that says that for large n, the variable properly normalized, it is indeed normal distributed. Okay, so these two examples, just to say careful, the distinction between randomness and disorder is, I mean, better to think a little bit and not to have an orthodox, how to say, point of view, because the things are much more subtle and rich than one would think. Now, all this now, I have to introduce you, Dr. Riemann. Now, in 1859 was the annus mirabilis of Bertrand Riemann, because he got, first of all, professorship in Göttingen, where he had studied before with Gauss, and after he went to in Berlin, and then finally go back to Göttingen. But more importantly, he was elected member of the Berlin Academy of Science. He has to produce a manuscript in that occasion. And he wrote the only manuscript of his production on number theory. And is the famous paper in which he tried to estimate how the number of prime less than a certain quantity goes asymptotically. Now, if you go to page 3 or so of the English translation, at least I have you find these sentences. It's very probable that they are all aligned this line. Of course, it would be desiderable to have a rigorous proof of this, blah, blah, blah. But I don't need it. Essentially concluded, I don't need it this time for what I have to do. Now he's talking about these zeros that, according to his conjecture, according to his idea, has to be aligned on the line 1 up. Now, Riemann hypothesis has a special status in mathematics, different from other probably even more famous mathematical theorem like the Fermat-Last theorem and so on and so forth, because having the Riemann hypothesis proved or disproved has a lot of consequences in many other branches of mathematics, and even in physics, I would say. There are beautiful connections also with random matrix, quantum chaos, general theory of phase transition, and so on and so forth. So I want to say that it's not a problem d per se in itself. It's something which has also a breadth behind it, and has consequences which can be longer reaching, let's say. Now, the subject has an enormous literature behind. And I want just to point out two standard, I would say two beautiful references, which is the book by Edwards, which is, even though it's a few decades ago, but is still an outstanding references. And then a series of other books, as this one I'm just presenting here. Now, after all this, let me tell then what is the Riemann zeta function. So it's this function of analytic variable S that can be defined equivalently for real part of S bigger than 1 in terms of a series and a product. And the origin of this identity mathematically is obvious, because the lowest prime is 2, so you can expand this binomial, and once you expand, you start collecting term of this infinite product, you find integer, and by unique theorem of arithmetic, there are all and only the integer of this kind. But for a physicist, this identity is even more beautiful, I would say, because this is an identity between ensemble. Consider a free bosonic system whose dispersion relations are the logarithmic of the prime. At this point, when you draw the energy levels, being bosonic, you can populate this level as much as you want. And so you realized that this identity is referring to the identity of microcanonical ensemble, which is on the right-hand side, and the grand canonical ensemble, which is on the left-hand side. Now, in this putative physical system associated to the Riemann zeta function, the density of states grows exponentially. So, of course, at a certain point, you start to compete with the energy, which was the logarithmic also. I mean, the exponential of the logarithm when you exponentiate. So, all this to say that should exist a nugget or temperature where the system blows up. So, the physical system associated to Riemann naturally is defined for low temperature, so up to S equal 1. If you want to know what's going on for larger temperature, for high temperature, you have to do analytic continuation. But Riemann was the master of analytic continuation, he invented. So he was able to find which kind of integral you have to do on the complex plane to define this function everywhere else beyond real part of S equal 1. And then he got a functional equation for it, which related the value of S, the value 1 minus S, which is kind of duality, with a prefactor which is completely explicit under your eyes. Now, I'm underlining this because when you use this functional equation to study the analytic structure, this function, the complex plane, what you had? You had the pole in S equal 1, which was the Hagedorn temperature, a bunch of zeros, which are certain. Let me use this adjective, namely, is under your eyes, was this sinus and gamma function that was before, that are all the integer even negative. And then there are a series of zeros, which Riemann conjectured to be on the axis 1/2. Even though the functional equation he derived, the only things you can conclude is that if there is an axis zeros here, should exist another one, 1 minus S. So the functional equation of Riemann does not imply at all that the zeros has to be on the line 1/2. How do we know that there are infinite number of zeros? Well, with a little effort, Riemann first and later von Mangold compute the logarithmic residue of this function. That, of course, compute the number of zeros minus the number of poles. But poles there are only one, so you can subtract it and get the number of zeros. And therefore, you realize that there is a number of zeros that grows with the height of these things. Therefore, in this critical strip, there will be infinite number of zeros when you increase the height of this interval. Now, the calculation of these zeros has attracted the attention of many mathematicians in the past. I just want to draw your attention. Also, Turing was trying to disprove the Riemann hypothesis and set up his own machine actually to do this calculation. But there are obviously become the kind of record that many groups, very gifted and with extraordinary power, computer power, enlarge more and more the number of zeros, always find them on the line 1/2. So this is a fact, at least the best that we know, that this line up to a certain point are on the line 1/2. Now, this is related also to beautiful story associated to quantum chaos, to random analysis, where I said where Michael Berry made a stunning contribution. I have nothing to say on this point, just to say that I read with great interest and fascination all these papers. Now, let me do, so I show you this, and you might wonder yourself, so where the hell is this randomness that I'm talking about? Where it is? It seems to be no place. Well, let me take the inverse of the Riemann zeta function. For real part of S bigger than 1, he has this expression, and then I expand the infinite product. But now something very important change with respect to the original case. Because when you start reorganize this term, it appears a Dirichlet series, of course, but the number of integers that appear are not all the integers. Start to appear only the square-free numbers. And the reason is that you had only one prime to get by any of these terms. You cannot get more than one. So of course, when you start multiplying, organize them, you get that the integer which appear in this series are the square-free numbers. And the residue, well, the sign in front, is 1 minus kappa. Indeed, the square-free number for a physicist cannot, a physicist cannot resist to associate the prime to a fermion and say that this way of looking the Riemann partition function is like the partition function which computed a fermionic average. So this is the fermionic number, essentially, of the. Now, to understand where the randomness this is, first of all, I express this inverse of Riemann as Dirichlet series, and then with a little trick, which is called a Abel resummation formula, but it's very elementary, you can express it like an integral, and the weight of this integral, which appear here, which is a Mellin, is the sum of all the coefficients which are here. Okay, so these are the rules. Actually, this will be the basic mathematical object I will deal later. Now, when you start looking how the mu are distributed along the sequence of square-free numbers, you get a sequence of plus and minus 1, which if I bring you in a point of this sequence, let's say 10 to the 60, you are completely unable to distinguish from a random sequence. This is my thesis. I have, of course, to prove it. I have to argue, but this is the idea. If it's so, when I start summing this bunch of plus and minus 1, and this is actually the actual sum, this mx, well, you realize that this function is really growing like square root of x. It's not a proof at all. I'm just saying, let me check. Let me see what's going on. Now, if this is so, namely, if I would be able to argue this, namely that this density grows like square root of x as it does a Brownian motion, well, this is a theorem of mathematics. The integral will diverge a real part of s equal 1/2, and therefore, the first singularity of the inverse, which the Riemann has 0, but 1 over x has pole, will be on the axis 1/2. And since you have duality, if you are able to arrive to 1/2 without encountering anyone else, all the zeros has to be on the line 1/2. Okay, so this is in a sense the line of argument. Now, as I said, is not a theorem. What I've just shown you is end wave argument. Now, you know that in mathematics, if you want to understand really things, what you have to do is to enlarge the panorama where these things live. Now, example. When people want to understand when a real function, a singularity, has to invent complex analysis, because only in complex analysis you understand why a series 1 plus x squared diverge in 1. As well as if you want to understand why the quintic, the algebraic equation, cannot be solved more than the degrees 5, well, Galois has to invent the group theory. And once you invent the group theory, everything becomes clear, even though before looks an oddity. Okay, so I'm taking here the same attitude, let's say the same general attitude to enlarge the original problem to Riemann to a huge, immense, infinite class of functions, where what I said before will appear more natural, more familiar, or say more obvious. So these functions are the so-called L function, Dirichlet L-function. Now, Dirichlet was a close colleague of Riemann and very good friend of him. He was the founder, actually, of the analytic number theory. And he was also in Göttingen, as well as Gauss, which is the other third great mathematician behind all these stories. Dirichlet posed the following problem. He said, well, I take an arithmetic progression which involves two numbers, which are called Q and H, is called the modulus and the residue. And then he asked, if I have this arithmetic progression, under which condition on Q, on the modulus and the residue, this sequence contains infinite number of primes. And amazingly enough, the solution was stunning simple. He concluded that Q and H must be co-prime, should not have common divisors. This is not only necessary, but also sufficient condition. Now, the example, just to make some fun, you take this, you generate these numbers. There are, of course, a lot of composite numbers, but there are primes. And Dirichlet claimed there are infinite number of them. You take another of this one, and once again, the same story. Now, the way of visualizing this is drawing a straight line with a slope given by the modulus and intercept by these things. And you start see where the prime appear on this sequence. And you realize, especially if you do a huge analysis, that they are equally distributed along this line. This will be a theorem later on. But at the moment, you just take an experimental fact. Okay, now what Dirichlet was doing is essentially condensed matter on arithmetics, because it takes a lattice essentially. So you have all the integers, it takes a lattice of period Q and make an arithmetics modulus Q, which was actually the things invented by Gauss. Gauss was the king of this kind of modular arithmetics. So for instance, our watch, when is modulus 12, but to do interesting mathematics, you should take the numbers which are coprime with 12. The reason is that if you take them, you can set up a group multiplication table with these numbers, which indeed is an abelian group made on the number with no common divisor with the modulus. The obvious, I mean, the reason why you cannot employ the other one is that if you take 2, for instance, 2 modulus 12 is 4, but 2 times 8 is 16, modulus 12 is still 4, and you do not have a group. So this is the reason. Now, when you have a group, this group has a dignity of a name. I mean, a great name is called the abelian group of prime residue class modulus Q, is abelian. And the number of elements is the so-called Euler phi function, which is the function which counts how many numbers coprime with Q there are less than Q. Now, it's obvious that if the modulus is a prime, the dimension of this group is Q minus 1, because all the number which up to Q is no divisor with Q itself. But if you take a composite number, like say 20, well, you have an interesting dimension of this group. Once you have a group, you can ask a reducible representation, but the group is abelian. So the reducible representation, first of all, are one-dimensional. Secondly, the number of the reducible representation are equal to the numbers, to the dimension of the group itself, because each element is a class of itself. So there are as many characters, as many elements of this group, and there are phases. These phases, so there are these arithmetic functions satisfy a series of properties. Very simple. They have to be, of course, periodic, because it's how we start. Has to be purely multiplicative. Has to be different from 0 if the number is coprime. And moreover, they have to be roots of a unity with this kind of root. I mean, is the number of elements that you have. So example, if I take the modulus to be 7, the phi 7 is 6. So the root of phi 6 is this omega. And I can employ this omega to construct the 6 different arithmetic functions which constitute the character. Okay? So these are arithmetic functions which has independent value up to 6, and 7 is 0, and they repeat periodically. Now, all this long story to introduce this because Dirichlet used this to construct this function. Now, notice a very important fact that among these characters, there is always the trivial representation where you take all the elements to be 1. So this is called principal character. So using this character, Dirichlet defined this this function, which admit, once again, series and infinite product representation, since key is multiplicative functions. The key are pure phases, as I was saying, and for a physicist, these are nothing else than partition function, free bosons, which has just an extra abelian charge. Now, noticed that the Riemann function is a very special case of this infinite number of functions, because correspond to take the modulus q equal 1. In this case, the character is only 1, has no multiplicity, is 1 forever. But if you take any other modulus, any, you can also define a Dirichlet function, which has a certain number of characters, blah, 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 blah. So this is the infinite class of function I'm talking about. Now, this function, Dirichlet found out the same duality property as before. The residue at the pole s equal 1 is interesting, because if you consider the Dirichlet function associated to the principal character, you find the pole as the Riemann, because it just sum all the one, sum all together, and you get the divergence of the harmonic series, essentially. But if you add other character, the sum of this root of identity sum to 0, and you have zeros. So this means that the Dirichlet L-function not associated to the principal character are entire function in the complex plane. It's only zeros. No singularity at any final region, okay? Only zeros. And therefore can also be represented in terms of infinite product and so on and so forth. As before, there are certain set of zeros which are trivial coming from the duality, and a certain number which are in this region where once again you can compute the logarithmic residue, you know there are infinite of them. At this point, there is the grand pictures. So once you have this huge class, there is the grand picture behind all of them. And this was formulated by Pilz, a mathematician in 1884, who say that the non-trivial zero of all the Dirichlet function, namely for any modulus q and any character, are all along the critical line place a real part s equal 1/2. Okay, so this is the generalized conjecture, which included the Riemann, because the Riemann are essentially the principal, the Dirichlet function associated to the principal character for q equal 1, but is extended to all these functions. Now, today in this talk, I will discuss the generalized Riemann hypothesis for non-principal character. The reason is that the principal character is really the tough cases, is rather technical, and is not really a topic for a colloquium, but rather for really a seminar between people really interested in these stories. But if you're interested really in these stories, you have to read this latest paper I was mentioning before, which I wrote with André Leclerc a few months ago. Okay, so this paper is devoted precise to the toughest case of this case. But today, I will concentrate it on all the other Dirichlet function not associated to character, to associate not to principal characters. Now, why this is simple? You will see immediately why. So the main idea is I have this function which are defined by infinite product, naturally for real part of S bigger than 1. Now, can I enlarge the domain of convergence of this function? Can I see how much I can push in the complex plane before meeting a singularity? So this is the idea, how much I can really push it. Now, being this representation for real part of S, I take the log. Now, this in general is a kind of delicate operation. Now, the log of a function has a singularity when the function has pole and zeros. But I'm telling you, the Dirichlet function non-principal character do not have pole, has only zeros. So this means the log is the ideal diagnosis to spot the zeros of this function. Because when this guy is a singularity is where the P is the singularity. So this is the reason why the story is slightly simpler. So when I take the log of this function, I expand it and I got this Dirichlet series, which involved the prime. I use the usual trick to express as a Mellin. And this kind, the weight of the Mellin is the sum of this angle, because the character are angle. However, look, computed on the sequence of prime. This is absolutely crucial, as you will see in a minute, okay? So I'm computing a cosine of angle, but in the sequence of prime, not in the sequence of natural. Now, if I would be able to show that this is a power law, in particular, this power law is square root of half, then of course, all the zero are on the critical line. So this is a theorem, I would say. There is no doubt about this. Now you might ask, but what about if you have logarithmic? Are you going to spoil this conclusion? Not at all. Because if you have a behavior like this, and you use this Mellin or inverse Mellin, how it's called, you will see that the singularity of the Mellin remain firmly at 1/2. The only thing the log does is just renormalize the residue, but never shift the location of this, okay? So, conclusion, if the large asymptotic behavior of this series proved to be an ideal diagnosis for the real part of the zeros. I have no control on the imaginary part at all. I can only tell you how much I can push inside before I can stop. But being a Dirichlet series, the first can be high as much as he wants. I will be stopped the real part of this series, okay? Now, let me now explain in a physicist's word why you should expect this. Now, take q equals 7. So these are the integers. The character depend on the residue, so let me talk about the residue. Now, if I ask, what about the residue of the integer with respect to q? Is absolutely boring sequence. 1, 2, 3, 4, 5, 6, 0. 1, 2, 3, 4, 5, 6, 0. 1, 2, 3, 4, absolutely boring. But what about if I ask, what is the residue of this sequence on the primes? And look what happened. When you start spanning the primes, the kind of residue you got start to appear random sequence. It's not random, of course, but it looks, I mean, it's not regular at all. And when you start looking on a larger and larger scale, you start realizing that there are a bunch of numbers popping up in all possible ways. So this is what I'm heading to. And to do that, I will rely on certain results that other people have done. So theorem, let's say, or presumed so. So I have to control this series, the series of the cosine of the angle, however computed on the primes. Now, what about this cosine, the term of this series? When you span the prime, you really notice that this angle is jumping in the most irregular way. So if you do just an histogram, you get this. This was done for very few sampling. Well, it looks pretty close to what you would got to a random distribution of cosine of angle, okay? Once again, it's not a proof at all, but I mean, it's suggestive that something is going on there. Now imagine I plot the sum and I plot them versus other series which I generate with really random number generators. So here I plotted together with other 7 functions. I generated summing this time random numbers. Are you able to distinguish which one is which? Not at all. It's completely confusing. Can be the red one, can be the black one, the brown one. I'm not going to tell you, but you are not going to spot either, okay? So it looks the story is going in a certain way. So let me control better now the property of this series. So I'm talking about this series that I should be able to argue it goes like square root of n. First of all, notice that all the terms of this series are order 1. So if you want to have something which grows really fast, you have to cooperatively and coherently sum many terms of the same sign. You cannot jump immediately to a large values with just one term, because you are summing term of order 1, which can be plus and minus 1. So if you want to have something, a fluctuation, extraordinary fluctuation should have a coherent sum of something. Now, as a matter of fact, Dirichlet, that was the famous theorem he got at that time, says that all the angle or the residue, which are the same, are equiprobable. Is a theorem proved by Dirichlet. Indeed, if you do some experimental mathematics, you find there are stunning. I mean, the violation of this is extraordinarily small and becomes smaller and smaller and smaller the more you go high. So essentially, I'm dealing with a dice, guys. I have a dice of Q phases, okay? I'm dealing with a dice that can come up in one of these Q phases. Out of this, the consequence is that the mean of this series vanish. Is a theorem. This is a theorem. Now, I claim that these variables are very weakly correlated. Now, you can once again try to understand. I mean, once again, you try, you see if something is going in the right direction or not. So what I did is standard. I just take this cosine of angle and I computed the correlation function of lag. How it comes about? Delta correlated. So it's 1 if there is no separation, zeros otherwise. Now, you say as a physicist, is really zeros? Of course not. When you enlarge, you see that the values are very, very small there. But what I discovered doing my analysis is that if I would have enlarged the size of my sampling, this guy will shrink. So this is a typical finite size effect. And as a matter of fact, I discovered that you can have a very clear idea what the correlation of this number are if you read a paper by two outstanding mathematicians that solve the following problem, pose the following problem. Imagine you have the sequence of prime and you say, I have the angle here at this number. What will be the next angle, the probability of having the next angle theta b at the next prime or theta c after kappa step? Well, amazingly enough, they were able to find this function. It's here under your eyes. So you see that to have equal residue is anti-correlated. There is -1. But to have different residue is correlated, is +1. But more importantly, there is one with this log n. N is the number of sampling that you put in this analysis. So they make a clear prediction what are the finite size effect of this. And I check to extraordinary precision this law. And the consequence is that if you go to large n, these residues are uncorrelated. And this is true for any kind of kappa tuplet, you can take it. So at this point, if someone tells you this as a physicist, that you have a series whose average is 0, the guy are uncorrelated, and so on and so forth, you would say all the moments of this guy has to be Gaussian, okay? However, there are two subtleties here. First of all, I'm not concerned with momentum, I'm concerned with the function itself. Now, when you have really random motion, you can refer to another theorem, which is due to other famous mathematician, who says how the fluctuation, what is the maximum size of the fluctuation. And this is a theorem, which is called the Theorem of Iterative Log. So it says that the sup, the maximum variation of this function cannot be larger, apart the square root of n, log n. Okay, so the sup is 1. So this is the epsilon I was talking to you at the very beginning. So this series is predicted, if the random theory is working, to go at most like this, cannot go worse than this, okay? Now, I have another problem though. I talk about average, but you can ask, what kind of average are you talking about? I mean, the series is completely deterministic. Now, all of what I said seems to conclude that these guys has to go like square root of n. But can I check or disprove this? Can I falsify such conclusions? So at this point, you face what is called a famous problem of statistical physics, which is the fact that you have only one sample to one instance, how to say, to sample. So you would say there is nothing to sample. Well, I mean, this is well known how to do it. Now, this problem, by the way, is very well known in data science, in data analysis, because imagine that you want to predict the meteor, and you take all the history of meteor. Well, it's just one. It's just a curve that you got it. You cannot say, please go back yesterday and see what is the probability that it rains or there is sun. As well as the other phenomena which you cannot turn the time back, okay? So it's very famous problem, and as a matter of fact, was at the basis really of the random walk physics. Because Jean Perrin, when he made this measurement of random motion in 1908, and he got the Nobel Prize in 1910, he was using ensemble average. So he generate many walk, and then he just made the statistical analysis. However, another physicist, Ivar Nordlund, some years later, he did a completely different approach. He take one droplet of mercurium and let it goes in water. At this point, he start taking snapshot of the same trajectory. So it didn't use many trajectories, just take one of them. But then he takes snapshot. And the value of Avogadro number that he got was 1%, completely comparable, if not better, with the prediction of Jean Perrin. So the problem of single Brownian motion trajectory is that you will use the infinite time series to generate your own statistical ensemble. So with an abuse of language, I would say the time series behave like its thermal bath. So what you have to do is, this guy is given. I cannot do anything about it because it's completely deterministic. However, I can chop it in many different ways I like it. I can sample them in many different ways. I can generate my own ensemble. This is very common in statistical physics. You say, I have a huge system, I take a portion of it, large enough such that blah, blah, blah. So I define what is called the block variable. So I take a huge interval, but finite in this. And if the original series goes like square root of lambda, the same should happen for any of these huge subsystems. Now, consider that I can average as much as I want, because this series is infinite. So I can span all the sequence of square free number and say, let me do the analysis on this interval, on this interval, on this interval, forever. It's just a question of patience and computer power. So with this attitude, I did really a huge battery of highly sophisticated statistical tests, really obsessive analysis. What I mean is 100,000 tests done all over the possible way I can get up in this sequence of integers. I arrived till 10 to the 20, and it took me 3 years to do this calculation in all possible ways. So there is a bunch of sophisticated tests to check if a sequence is random or not, which come from the National Institute of Standard Technology of the United States, as well by specialized text in data analysis. Well, all these tests, all show that the sequence I'm talking about is completely indistinguishable from a random series, completely. So let me tell you a few examples. I did, for instance, this. I take part of the portion of these sequences, and then I start from the origin and compute where is the time mean where these things reach its minimum, and then its maximum in an interval t. Now you can ask, what is the distribution of t mean? Now this function is being computed in probability, assuming that is a random walk. And you find the result in the famous book by James, The Theory of Probability. Well, this is the function, this is my data. If I go and make test of goodness, I mean, the goodness of these things, I find for many different, I'm average, typically a key values, which is 33 for 35 degrees of freedom, with attendibility, how to say, probability of validity 0.66, which is extraordinary numbers. Now, if you do the Kolmogorov-Smirnov test, which is even better to check if a function satisfies, the data satisfy a certain function, I got a degree of confidence of 99.99%. Okay. Now, if I ask what is the distribution of the time separation between these two guys, now this is a very complicated function, which has been recently computed by the group in Paris. So you can see it's really a respectable function, I would say. Now, when I compare with my data, once again, I have a way of saying, well, the agreement is stunning, 99.99%. And this persists forever. So let me just make the last example. I can compute the variance of this block variable. I can compute analytically because I have enough information to do it. And I have a prediction. I have a prediction that you see involves several log all along the way. But one stunning prediction is that this quantity should be completely independent of the modulus. Namely, I can take any Dirichlet function, I shall always find the same. Is it true? I did this for many Dirichlet functions, stunning universal curve. All of them align uniquely on this line. Level of confidence, once again, stunning. The Kolmogorov test give me 99% that the data really fit these stories. Now, I don't want to bother you with other of these things. I just want to tell you that I did innumerable number of tests, but not only innumerable. I repeated 100,000 times, and each time with the same result. So I never find any discrepancies that allow me, if I show to someone else, are you able to distinguish it, which one is random, which one is coming from the Dirichlet? You are unable to do it, okay? Now, I even did the distribution of the function itself. So to whom the bell tolls. So I did the distribution of the function itself. And when you go and ask how good this fit is, you find stunning p-values, okay? So these p-values, as you know, are the ones which tell you, yes, what is your hypothesis is very well satisfied. So with all that, I would say that this function based on theorem, some part of the control of this function come from some theorem, some mathematical result, has to go like this. It's very universal, it's very simple, the theory is very elegant, and is, how to say, you can falsify it. And I was never able to falsify it. And actually you have a reason to believe that if I would be able to go larger, things would even go better, because the finite size theory that I show you tell you that this will decrease. And actually check it, that is going the right way. So if this is so, there is no other chance, but the integral will be singular at 1/2. But at this point, all the zeros will be on the critical line, because I have the duality relation. If I was able to push this analytic continuation up to 1/2, with never been stopped before, all of them has to be on the line 1/2. So the conclusion I have to say here is that, first of all, there are infinitely many functions which, as the Riemann, has their zero along the line 1/2. So this is somehow make the mystery, let me call, it's not mystery, make the story of Riemann part of a bigger panorama. These properties can be traced back to some random property of the primes. Better, more than random properties of the prime, the random of the residue with respect to the prime, which are ruled by theorem, as I told you before. So the validity of this generalized Riemann hypothesis, in my opinion, therefore, at least the approach I show you, seems to be really a very nice result of probability theorem, which involve the residue and the absence of their correlation. And there, after all, I would say that can be indeed considered as one very nice example of random walk theorem. Thank you very much for your attention.
Thank you very much, Giuseppe, for the nice talk. So at this point, I think we can have some questions. And what I would ask maybe is if people could raise their hand in the chat, or maybe, yeah, raising the hand in the chat is the simplest thing, and then we can basically try to proceed a little bit with order. So any questions from the chat? In the meantime, while people think of questions, I have one myself. I'm certain that you also presented this to mathematicians and experts of the fields. So what was the reaction? What is the comment on, for instance, whether this can sort of give them some new idea on something to try to prove, or something that maybe was looked at in the past already? I mean, of course, this is a field with an enormous history as well, right? So what do practitioners of the field say?
Yeah. No, thanks for the question. Okay, first of all, let's say it's also a question which has a sociological side. Let me put it this way, because you see this approach was strongly based on kind of argument, way of arguing that is physicist-like, I would say. Probably a mathematician will be horrified. Now, consider one thing. The exists a branch which is called probability number theory, and there are distinguished members of it. I mean, Mark Katz was one of them. Erdős was another one. Nowadays, Terence Tao and many others. Now, I didn't have a chance to talk to Katz. I would have liked it, but no way. Erdős as well. Terence Tao, I didn't have a chance. And I would say that the honest answer is that I didn't have really chance to get through, I mean, to a serious discussion about that. However, the reaction is, as I told you, there are an orthodox point of view, which say, well, after all, the Riemann is Riemann. I mean, there is no randomness in it. Yeah, but consider that there is no theorem which prevents the deterministic sequence to behave as a random. I mean, I just want to underline this, okay? So there is no abstraction in principle. And moreover, there are a beautiful result of mathematics, which I didn't have time to present it, which says that there are infinite random functions, purely random, which are completely different at the complex plane, but they share exactly the same zeros of Riemann or Dirichlet. So this result, due to Grosswald and Schnitzer in the late 50s, I guess, put my argument even in different contexts. I could have tell you the stories really in a space of random functions, purely random functions. So this probably will acquire more dignity, let's say, in the field of probability. But there, as I said, I don't claim anything. I mean, I presented what I told you with all the way of arguing of a physicist. I'm not a mathematician, and that's it. I mean, probably someone else will be able either to disprove me or to make more rigorous. I'm not able to.
Okay, thank you. So in the meantime, there is a question from Michael Berry, who can unmute and just ask the question. Please go ahead.
Michael, I cannot hear you.
Michael, I think, yeah. Did you unmute, Michael?
Just a second. Good,
Yeah.
Yes. Can you hear me now? Yes. Giuseppe, thank you for a very nice talk. It's a very beautiful presentation. But, and you know there will be a but, I want to ask you this. Now, mathematicians already know a number of very sophisticated things about the zeros. They know, and you quoted this, that at the moment, the first 10 trillion zeros lie on the line. They also know that infinitely many of them do. And they also know that at least 42% of them do. Now, what I want to know is this. If the Riemann hypothesis is false, then there would be some zeros very high off the line. Now, how high would they have to be in order for all the tests that you've done to still lead to the result that you presented to us? In other words, what do these tests that you do tell us that the mathematicians don't already know? I mean, just to add another thing, suppose mathematicians would prove that 100% of the zeros lie on the line, and that's the best that you could do with the methods that you're telling us. That still would not prove the Riemann hypothesis, because this would not exclude a set of measure zero being off the line. And phenomena like this do occur in mathematics. And one could argue, I don't, but one could, that the reason why the Riemann hypothesis is so difficult to prove is that it isn't true, but it's nearly true in the 100% or so. So how do you, I mean, the specific question, how high must a zero off the line be to falsify the Riemann hypothesis, but still satisfy all the tests you've done?
Yeah, thank you very much, Michael, for the question, which indeed is the question. So as you said, a lot is known about the zeros, their density, at least bound of them. What is called the zero density theorem, which says that if there are zeros outside, they are infinitesimal with respect to the others, and so on and so forth. Absolutely stunning things. Now consider the following things, which I think is the strongest of my argument. I can never prove, I can never convince you, even if I would have done 10 to the 3 billions analysis, because this doesn't prove anything. I mean, we know it. There is an however, though. This is by however. The however is to have a zeros outline, you should change drastically the behavior of an infinite series, which is like why the hell you have universally the Bell distribution? Why the hell we have universally the central limit theorem? You had under very, very, very general condition. You can take many samples, you always find the same. You remember I mean, I know I'm sure you know the famous article by Wigner when he was trying to say the occurrence of pi. And I said, well, you take the Bell, it occurs pi. I said, my God, how pi is the circle? So the normal law distribution is extremely rigid. You should convince me, vice versa, that you are able to find a teeny epsilon which is spoiled these exponents 1/2. How come? You should have correlation or really long range that I never see in any of my simulations. So I'm not, my simulation, we can never convince anyone. And I'm the first to admit it. But at the same time, no matter how I span, no matter how enlarged, no matter how chop it, no matter which test I did it, I never experienced any correlation ever. And you know that this series a certain constraint. The sum has to be equally distributed. The correlation is according to what other result implies. So if it is disproved, you are violating the normal law distribution, which to me, that would be stunning. That would be absolutely stunning. I mean, how the hell this guy is not 1/2, but 1/2 plus something, this something, what it is? It should come from correlations. But where do you can get this correlation? You know, when you make the inverse of Riemann, you're just picking randomly prime and you're organizing them according to plus and minus. Now, the only way you can take this prime randomly, and this will be completely random. So the only correlation can come once you have taken these square free numbers, you start ordering them. Because at this point, you're not any longer random, but you are ordering. And you might ask, well, I knew this is plus, so the next might be minus. But if I would have taken random, you can never guess. Now, this kind of correlation, I could check, first of all, if it exists up to a certain scale, and I never observed it. But then there are mathematicians that has tried to work it out, this kind of correlation, as a solid prediction. And they say this is a finite size effect. I tested how it's called with log n, and a beautiful fit. So once again, as a physicist, I should be open to say maybe, but at the same time, I have billions of reasons to say can never be. You see what I mean? I mean, I cannot convince in a positive way, but at the same time, the opposite is so improbable that would be really stunning to observe.
Well, if I may continue just a little, I don't want to monopolize this. There is a possible route to really proving, and this would be, you know it, it's if we could prove that these zeros with respect to the line will be the eigenvalues of some Hermitian operator. Now, of course, you know this. Now, we know a lot of properties of what this operator must be like, and you can test this, and you can prove, you can, for example, derive that random matrix theory has its limits. It doesn't apply at certain ranges, and we test it numerically, and this is true, and this looks convincing, and I would say it gives insight in the same way as your arguments give insight without being a proof. However, there is something peculiar in this quantum argument, because there are certain features that don't quite fit, which either could be interpreted as being that if the Riemann hypothesis is true, the operator is very, very subtle in a very strange kind of quantum system, or that the Riemann hypothesis isn't true and that some sufficiently high distance up the critical line, you would find that a zero isn't there. And you know, I'm agnostic on this point. And if we would find a zero off the line, then what would become of these arguments of yours and of mine, which is suggestive? Well, we would learn something. We would learn why it is that the Riemann hypothesis is almost true, but not quite. You know, Einstein said God is subtle but not malicious. But then God would be malicious if there were to be a zero or some number of them off the line extremely high. So, I mean, the person you should talk to, maybe you tried, is Andrew Lisko. You know, who did these.
Well, I mean, I didn't try, but yeah, this is
obviously. Because he's, I mean, you see, when I met him, the first thing he said to me is, "Why do you physicists all believe that the Riemann hypothesis is true?"
Yeah.
And now, exactly hits the point that you make.
Yeah. No, indeed, this will be the ideal person to talk to. Thank you for the suggestion.
Yes.
Let me say that the spectral approach to the Riemann function is absolutely fascinating and really stunning. Let's say the fact that not the weak point, I don't know how to say it. The fact is that we know, first of all, that these zeros are random. So the chance that you get really the right Hamiltonian looks to me quite something. Yeah. My approach, in a way, what is the strength? The strength is simple, elegant, and universal. It applied to all the Dirichlet function. You had the problem, sorry, it's not you, the guy that want to have the spectral theory to find each Hamiltonian for each Dirichlet and has to prove it.
No, just a moment, because the spectral approach, as we understand it, is very similar, because all quantum systems which have chaotic classical counterparts would have the same type of randomness, namely random matrix theory up to a certain point and then a different distribution thereafter. But you can say precisely what distinguishes one from another. So there is also a kind of universality within which the Riemann would be embedded. See, I don't see these approaches as being in competition to each other.
No, indeed.
Because
there
I think
two sides. I mean, in my opinion, provide valuable information from two different points of view.
They give insight. Both,
yeah,
yes.
Indeed, you know that if you use the location of the zeros along the line, you can define another function which admit a series in trigonometric with the frequency which are the location. That if the Riemann hypothesis is true, should have a peculiar behavior. So I mean, this is and from this other side looks mysterious outcome, right? Seems another stunning consequences. So indeed, the two approach provide a really extraordinarily valuable property of all this class of function. I don't see any competition, just two different point of view. I mean, two different way of understanding why they should be on the line one half, you see?
Good.
From the Brownian motion point of view, it's just related to the universality of any Brownian motion. That's it, finished. I can tell to a first year's graduate students, these things. So he can check it actually. He can do these things. I remain stunned by the goodness of all these tests.
Thank you very much, not only for the question, but for the very nice discussion. There is another question by Masahito Yamazaki. So please, Masahito, go ahead.
Yes. Thank you, Giuseppe, for a beautiful presentation. So, well, my question is that, let's see. So, what is the relation of your discussion with the discussion in random matrix theory? I mean, I remember, for example, Freeman Dyson had a paper about describing random. So is it something you can translate to your discussion back to random matrix, or going back and forth, or is some aspect very special to more in Brownian motion? Or
look, thank you for the question. It was what we were discussing before with Michael, namely, there should be a relation. Let me put it this way. However, it's not so obvious. It's not so obvious at all, because I'm concerning directly with the sum of the coefficient of this function, this Dirichlet function. On the other hand, the random matrices make a much more complicated object. They have to compute the zeros of these functions, which is complicated business. You have to use the Riemann-Siegel formula and so on and so forth, and then see how they are distributed once you properly normalized. So you see, they have to be related, because it's like if I give you a polynomial function, of course, the coefficient determine that zeros and vice versa. But it's not so obvious to relate the two sets of data. It's not immediate, let's say. I'm pretty sure it can be done, but I'm not the guy to do it. Sorry.
Yes, I think I should make a comment about this, if I may. I mean, this is to the questioner. It was a very brilliant insight of Freeman Dyson to make this connection. But we're well beyond that now, because we've known since the 1980s that random matrix theory only applies to relatively close lying zeros of the Riemann zeta function. As you go higher up the line, the range of zeros to which the random matrix theory gives good predictions for the statistics does grow, but it grows much more slowly than your height up the line. And if you go beyond this range, we know exactly what the statistics are, and they deviate from random matrix theory. So random matrix is a part of the story, but we know from the 1980s that this what its limits are. And the limits, by the way, are precisely what distinguishes a random matrix from a spectrum of a classically chaotic quantum system. So this is what our emphasis is based on, this observation. And there's an analytical argument, and it's supported by numerics that we did using Oblisco's in the 1980s. So random matrix theory is part of the story, but not enough.
Okay, yeah.
I see. Thank you so much for the clarification.
Yeah, yeah.
Well, thank you very much, Giuseppe and Michael, for the answers and the nice discussion. Are there? Yes, there is another question from Abiram. I'll ask him to unmute.
Hi, am I audible?
Yeah.
Okay, so thank you for the fantastic lecture. I have a question regarding the repulsion of the zeros of these different L functions. Is there, perhaps you might have mentioned it, but is there like a universal physical principle as to why or what causes the repulsion between the zeros of these different L functions?
Well, I mean, the naive question is that since correspond to non-integrable system, to chaotic system, so in general, you expect energy line of this system not to cross. I mean, this is the naive question. And but as I said, I do not analyze where they are. I have to make clear this. I never concern where they are on the line. I'm concerned they are on the line, but not where about it. Mm-hmm. So I just, how to say, propose a set of arguments. We show why they should be on the line 1/2, but I'm unable to say where they are along this line. So this is what I call somehow the horizontal approach. So I try to push and see where I shall stop. But where I shall stop doesn't depend where the first singularity are. It can be high as billion or can be 0.5. I always be stopped at 1/2. So I'm concerning why they are all on the line 1/2. Now, once you know that they are on the line 1/2, you can take either the approach to study how they are distributed and so on, or vice versa. That's what Michael was saying before, taking instead as a principle to say, look, if I spot an Hermitian operator where indeed these are the eigenvalues in the proper unit, I mean, you have to subtract 1/2, divide by I, the reality of these things will prove that they are all on the line 1/2. But I'm stressing, I'm not taking the point of view, analyze each of them where they are. I don't know, simply I don't know where they are. But I can tell you that if there is a Brownian motion construct on the coefficient of this function necessarily should have all the zeros on the line 1/2. This is what I'm saying.
If I may, just for one moment, if I can also answer the question in a different way about the repulsion. This is within the range of random matrix theory, but it's much more primitive than that. You see, if it's correct, the suggestion from looking at some of the formulas for the zeta function and comparing with quantum mechanics, that there is this underlying quantum system, it will not have time reversal symmetry. And there's a theorem of Wigner and von Neumann that the degeneracies of such systems require 3 parameters, not 2. Now, and this implies directly, and it's an argument I gave in 1980 or 79 even, it implies directly that level repulsion is quadratic, which is exactly the random matrix relevant result, and it's what's found for the Riemann zeros, and that explains why you get pairs of zeros extremely close together. Now, if they would be off the line, then sometimes you would have 2 complex zeros. But the fact that you don't is supported by this codimension of degeneracies argument, which leads directly to the number of very close lying zeros with the repulsion law, which is quadratic, exactly as observed. So it's to do with the codimension of degeneracies of systems without time reversal symmetry.
Yes.
Thank you very much. We have another question from Alfonso Lanuza. I will ask him to unmute. Please go ahead.
Hello. Thank you very much for the talk.
Ciao.
It was very nice. I happen to be a physicist as well, but I also have been obsessed with the Riemann hypothesis for many years. And my question would be, if I try to publish, right, some of the results that I found, what is the best way to go? Because this is a field that has a lot of opposition and is...
I don't know. Sorry, I don't know how to answer. No idea. Well, depends. You see, depends what you are looking, depends what you are studying. No. Yeah. Honestly, I have no idea.
So is there someone you could recommend me to enter in contact with to see if my results are really novel? Or
depends which aspect you are interested in, which kind of results you had. I mean, there are many really, I mean, pose the way you pose, I really have nothing to say. I mean, because you might have, I don't know, brilliant idea why this and that, but then for some reason, which I don't know, you might submit to, say, physical journals. I mean, many people I can see in the audience, Michael himself, Hermann and so on, Sierra and so on, they had a stunning, beautiful idea how to check this, how to make in cold atom, in radiation, in antenna, such things, beautiful. So you can submit to journal, physics journal. Otherwise, book, I don't know. I mean,
yeah, my ideas are formally purely mathematical. I have no connections with physics.
Yeah, so I don't know. Sorry, I mean, I would like to help you, but I have really no idea what to comment.
Yeah, it's a little bit more of a sociological or meta issue, as we would say.
Yeah.
Thank you anyway for the question. Are there any last question, perhaps, since we are a little bit, no, I don't want to say running late, but there have been quite plenty. Or any last comments, perhaps? Well, if not, I think on behalf of everybody, I would like to thank Giuseppe, and also I would like to thank all the people that intervened in this very lively discussion at the end. It was very, very nice. So thank you, Giuseppe, for the talk, for the discussion.
Thank you for all of you. Thanks for attending the talk. Yeah. So hello, everybody. I hope to see you in presence very soon. I hope so.
Yes. Yeah, thank you very much, Giuseppe.
Ciao, Michael. Very nice to see you. Yeah.
And you too.
Yeah.
And let me just say, to conclude, that the talk will be on the GGI website. And I think that there will be a possibility to ask questions also on the GGI, which we will then forward to Giuseppe. Mm-hmm. So if people that are watching this as a recording might have some questions, that might be a chance to ask Giuseppe. We will.
I will be pleased. Yeah. Thank you.
Well, thank you again.
Okay. Thank you, Alessandro. Thank you. Thank you, the GGI, for the ciao, Stefan. Thank you to you for the invitation, and yeah, hope to see you soon. Yeah.
Hope to see you soon.
Yeah. Okay.
Okay. Thanks,
Bye.
Giuseppe.
Bye.
Have a nice evening.
Yeah.
Ciao a tutti.
Bye bye.
Ciao a tutti.
Ciao.